To effectively prepare for the Alabama Electrician Exam, dedication of a specific amount of time each day for studying, such as 2 to 4 hours, is essential. Prioritize the sections of the Mike Holt exam prep book based on their importance and your areas of weakness. Begin by reviewing the tables and key concepts in each chapter. Develop a solid understanding of the basic principles of electricity, circuits, installation methods, and safety practices. Concentrate on the most common topics covered on the exam, which typically include Ohm's law, wire sizing according to the National Electrical Code, and proper grounding techniques. Implement active recall methods by reading through the material and then attempting to recall the information without looking back at the text. Utilize practice questions or online simulations to test your understanding of the concepts. After completing the practice questions, thoroughly review your answers and identify areas where you need more clarification or further study. Employ visual aids such as charts, diagrams, and flashcards to aid in memorization of key concepts and formulas. Create and use mnemonics to remember key formulas or concepts, for example, E equals I times R for Ohm's law, or BUG for branch circuits, underground, and grounding. Take regular breaks during your study sessions to prevent burnout and maintain focus. Review the material you have studied at the end of each session and also before starting the next one to reinforce learning. Before the exam, go over any highlighted notes or important points to refresh your memory. Consider joining a study group to collaborate with fellow students, share knowledge, and prepare together. Attend online or in-person exam prep courses that provide guided instruction and supplemental materials. Practice with past exam questions to familiarize yourself with the format and types of questions that may be asked in the actual exam. It is important to approach the exam with a calm and confident mindset, believing in your abilities. Electrical theory is based on fundamental concepts that are crucial for understanding how electrical systems work. Ohm's law, expressed as voltage equals current times resistance, is the cornerstone of circuit analysis. Understanding this relationship allows for calculation of voltage, current, or resistance in a circuit if the other two values are known. Series circuits are characterized by a single path for current flow, meaning the current is the same at all points in the circuit. The total resistance in a series circuit is the sum of individual resistances, and the total voltage is the sum of the individual voltage drops across each resistor. Parallel circuits, on the other hand, provide multiple paths for current flow. The voltage is the same across all branches in a parallel circuit, and the total current is equal to the sum of the branch currents. The reciprocal of the total resistance in a parallel circuit is equal to the sum of the reciprocals of the individual resistances. Power, measured in watts, is the rate at which electrical energy is transferred in a circuit. It can be calculated using the formula power equals voltage times current, or by using variations such as power equals current squared times resistance, or power equals voltage squared divided by resistance. Understanding power calculations is important for determining the appropriate size of circuit breakers and conductors. Conductors are materials that allow electric current to flow easily. Copper and aluminum are the most commonly used conductors in electrical systems due to their high conductivity and relatively low cost. The size of a conductor is determined by its ampacity, which is the maximum amount of current it can carry without overheating. The National Electrical Code, or NEC, provides tables that specify the ampacity of different sizes and types of conductors based on factors such as insulation type, ambient temperature, and the number of conductors in a raceway. Insulation is a non-conductive material that surrounds a conductor to prevent electrical current from flowing where it is not intended. Different types of insulation are rated for different temperature and environmental conditions. Common insulation types include THHN, THWN, and XHHW. The NEC specifies the appropriate insulation type for various applications based on factors such as moisture, temperature, and exposure to chemicals. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. A circuit breaker is a device that automatically interrupts the flow of current when it exceeds a predetermined level. A fuse is a one-time use device that melts and breaks the circuit when the current exceeds its rating. The NEC specifies the appropriate size and type of overcurrent protection device for different circuits based on the ampacity of the conductors and the type of load being served. Grounding is the process of connecting electrical equipment and systems to the earth to provide a low impedance path for fault current. Grounding helps to protect people from electric shock and to prevent damage to equipment in the event of a ground fault. The NEC requires that all electrical systems be properly grounded, and it specifies the methods and materials to be used for grounding. Bonding is the process of connecting together all metal parts of an electrical system to create an electrically continuous path. Bonding helps to ensure that all metal parts are at the same potential, which reduces the risk of electric shock. The NEC requires that all metal parts of an electrical system be properly bonded, and it specifies the methods and materials to be used for bonding. Wiring methods refer to the ways in which electrical conductors are installed and supported. Common wiring methods include conduit, cable, and raceway. Conduit is a rigid or flexible metal or plastic tube used to protect and route electrical conductors. Cable is an assembly of two or more conductors enclosed in a sheath. Raceway is a metal or plastic channel used to support and protect electrical conductors. The NEC specifies the appropriate wiring method for various applications based on factors such as location, environment, and voltage. Electrical boxes are enclosures used to house electrical connections and devices. Boxes must be sized appropriately for the number and size of conductors they contain. The NEC specifies the minimum size of electrical boxes for different applications. Lighting is an important aspect of electrical design. The NEC provides requirements for the installation of lighting fixtures and the control of lighting circuits. Lighting calculations are used to determine the appropriate number and type of lighting fixtures needed to provide adequate illumination for a given space. Motor circuits require special considerations due to the high inrush current that occurs when a motor starts. The NEC provides requirements for the sizing of conductors, overcurrent protection, and controlled devices for motor circuits. Transformers are used to step up or step down voltage in electrical systems. The NEC provides requirements for the installation and protection of transformers. Special occupancies, such as hazardous locations, require special wiring methods and equipment to prevent explosions and fires. The NEC provides detailed requirements for electrical installations at hazardous locations. The National Electrical Code, or NEC, is a comprehensive set of standards for the safe installation of electrical wiring and equipment. It is updated every 3 years and is adopted by most state and local jurisdictions in the United States. The NEC is not a law, but it is often adopted into law by state and local governments. It is important for electricians to be familiar with the NEC and to follow its requirements when installing electrical systems. Chapter 1 of the NEC covers general requirements, including definitions, rules for electrical installations, and requirements for examination and approval of equipment. Chapter 2 covers wiring and protection, including requirements for conductors, overcurrent protection, grounding, and bonding. Chapter 3 covers wiring methods and materials, including requirements for conduit, cable, raceway, and electrical boxes. Chapter 4 covers equipment for general use, including requirements for lighting fixtures, appliances, and motors. Chapter 5 covers special occupancies, including requirements for hazardous locations, healthcare facilities, and recreational vehicles. Chapter 6 covers special equipment, including requirements for elevators, escalators, and electric signs. Chapter 7 covers special conditions, including requirements for emergency systems, standby power systems, and fire alarm systems. Chapter 8 covers communications systems, including requirements for telephone, data, and cable television systems. Chapter 9 contains tables and examples that are used to apply the requirements of the NEC. When studying the NEC, it is important to understand the definitions of terms used in the code. The NEC defines terms such as ampacity, voltage, grounding, bonding, and overcurrent protection. It is also important to understand the organization of the NEC. The NEC is divided into chapters, articles, and sections. Each section contains specific requirements for electrical installations. To effectively use the NEC, it is important to be able to quickly find the relevant sections that apply to a particular installation. The index of the NEC can be a helpful tool for finding specific requirements. It is also helpful to become familiar with the general layout of the NEC so that you can quickly locate the chapter and article that cover a particular topic. In addition to the NEC, there are other codes and standards that may apply to electrical installations. These include state and local building codes, as well as standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to be familiar with all of the codes and standards that apply to your work. When preparing for an electrician exam, it is important to review the fundamental concepts of electricity, including Ohm's law, series and parallel circuits, power calculations, and conductor sizing. It is also important to be familiar with the NEC and to be able to apply its requirements to various electrical installations. Practice exams can be a helpful tool for preparing for the exam. These exams can help you to identify your strengths and weaknesses, and they can also help you to become familiar with the format and types of questions that will be on the exam. When taking the exam, it is important to read each question carefully and to make sure that you understand what is being asked. If you are unsure of the answer to a question, it is often helpful to eliminate the obviously wrong answers and then choose the best answer from the remaining choices. It is also important to manage your time effectively during the exam. Don't spend too much time on any one question, and be sure to answer all of the questions that you can before the time runs out. Remember to stay calm and confident during the exam. Believe in your abilities and approach the exam with a positive mindset. By following these tips, you can increase your chances of passing the Alabama Electrician Exam. Furthermore, understanding the nuances of conductor selection is crucial. The ampacity of a conductor, as dictated by NEC Table 310.16, depends not only on its size but also on its insulation type and the ambient temperature. Directing factors, as detailed in NEC Section 310.15, must be applied when multiple conductors are bundled together or when the ambient temperature exceeds 86 degrees Fahrenheit or 30 degrees Celsius. For instance, if you have 4 to 6 current-carrying conductors in a raceway, you must stare at the ampacity of each conductor to 80% of its listed value. Similarly, for 7 to 9 conductors, the directing factor is 70%. Selecting the appropriate overcurrent protection is equally vital. Circuit breakers and fuses protect conductors from overloads and short circuits. The general rule, as stated in NEC Section 240.4, is that conductors must be protected at their ampacity. However, there are exceptions, particularly for motor circuits and certain types of equipment. For example, small conductors such as 14 American wire gauge or AUG copper wire are typically protected by a 15 amp circuit breaker, while 12 AWG copper wire is protected by a 20 amp circuit breaker. It's also important to understand the concept of interrupting racing, which is the maximum fault current that a circuit breaker or fuse can safely interrupt. The available fault current at a given point in an electrical system must be less than the interrupting rating of the overcurrent protection device. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current, allowing overcurrent protection devices to quickly clear a fault. Bonding ensures that all metallic parts of an electrical system are at the same potential, reducing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding in Articles 250 and 250.100. For example, the size of the grounding electrode conductor, which connects the grounding electrode to the equipment grounding bus, is based on the size of the service entrance conductors, as specified in NEC Table 250.66. Similarly, the size of the equipment grounding conductor, which connects the metallic parts of equipment to the grounding system, is based on the size of the overcurrent protection device, as specified in NEC Table 250.122. Wiring methods vary depending on the application and the environment. Common wiring methods include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IMT, flexible metal conduit, or FMC, and non-metallic conduit, such as electrical non-metallic tubing, or ENT, and rigid polyvinyl chloride conduit, or PVC. Each wiring method has its own advantages and disadvantages. RMC provides excellent physical protection but is more difficult to install than EMT. FMC is flexible and can be used in tight spaces, but it is not suitable for wet locations unless it is liquid-tight flexible metal conduit, or LFNC. The NEC specifies the allowable uses and restrictions for each wiring method. For example, EMT is generally permitted for use in dry locations, while RMC is permitted for use in both wet and dry locations. When installing electrical boxes, it's important to select the correct size box for the number and size of conductors entering the box. The NEC specifies the minimum box fill requirements in Article 314. The box fill calculation takes into account the number of conductors, the number of device yokes, the number of equipment grounding conductors, and the number of internal cable clamps. Using a box that is too small can lead to overheating and potential fire hazards. Lighting calculations are used to determine the appropriate number and type of lighting fixtures needed to provide adequate illumination for a given space. Factors to consider include the size of the space, the reflectance of the surfaces, the type of task being performed, and the desired light level. The light level is typically measured in foot candles or lux. The Illuminating Engineering Society, or WISE, provides recommended light levels for various tasks and spaces. Motor circuits require special considerations due to the high inrush current that occurs when a motor starts. The NEC provides detailed requirements for motor circuits in Article 430. The size of the conductors, overcurrent protection, and control devices for a motor circuit must be based on the motor's full load current rating, as well as the motor's starting current characteristics. Transformers are used to step up or step down voltage in electrical systems. The NEC provides requirements for the installation and protection of transformers in Article 450. Transformers must be protected from overloads and short circuits, and they must be properly grounded. Special occupancies, such as hazardous locations, require special wiring methods and equipment to prevent explosions and fires. Hazardous locations are classified based on the type of hazardous material present and the likelihood of an explosion or fire. The NEC provides detailed requirements for electrical installations in hazardous locations in Articles 500 through 516. These requirements include the use of explosion-proof equipment, intrinsically safe circuits, and other specialized wiring methods. By thoroughly understanding these key concepts and diligently studying the NEC, you can significantly enhance your preparation for the Alabama Electrician Exam and increase your confidence in your abilities. Remember to prioritize your study time, focus on your areas of weakness, and practice. And of course, stay calm and believe in yourself. You've got this.